Hello and welcome to StrathSEDS Flight Readiness Review for the Mach-23 launch competition. We'll jump right in. So we don't have a confirmed list of the members attending the competition yet, as we're still awaiting a lot of us on internships and interviews and all that sort of thing. So we haven't got nailed down summer plans, unfortunately, but we're hoping in the next couple of weeks we'll have a full list of everyone attending. I'm the team lead for this competition and our sub-team leads are unchanged from previous design reviews. As is our overall mission statement, which has remained the same since PDR. I'll leave it there for you to read, but now I'll pass over to Pablo, who's going to be going into a little bit more depth on all of this.
Hi, I'm Pablo, and I'm going to be taking you through a summary of our launch vehicle and payload. Looking at the launch vehicle, the key design principles haven't changed from CDR. We're still using an L2375 single stage dual deployment. That's the concept. Our COTS flight computer has changed, however, from the CATS Vega to egg timer quasar, and the body diameter has increased from 5 to 5.5 inches to make use of some tubes that we had available. Similarly, our payload concept hasn't changed much since CDR. The biggest change being that we switched from linear springs to torsional springs in the actuation of the arm mechanism. This was done to improve the amount of force and save space. Here's an overview of our rocket, annotated in detail the key parts. It can be noted small but key details such as the shear pins and rail guides that are included here. The CANSET design also has not changed much, but however here is annotated. Here you can see the torsion springs, which have replaced the linear springs, and it should be noted that the activation of the solenoids, which allow the deployment of the solar arms, is controlled by the payload computer using pyro channels, which could be used for pyro, but are not being used for pyro. They're only controlling solenoids. Looking at an overview of our recovery system, the key computer has changed from the CATS Vega to the egg timer quasar. This was because of cost and increased flight heritage for the quasar compared to the new CATS Vega. We've received those parts and they're waiting to be assembled as a kit. Looking on the right, we can see a ConOps diagram of our planned flight profile, rising up to an apogee of 3,000 meters. We'll deploy the nose cone and the drogue chute, which also allows the CANSAT to be released, which then descends on its own parachute. And then after reaching 300 meters, the aft separation event occurs and the main parachute is deployed, allowing the whole rocket to descend down in a safe manner to the ground. Looking forward, I'm handing you over to Isaac, who's been doing some really great work on parachutes and our recovery system in general.
Hi, I'm Isaac, and I'm here to talk to you about parachutes. So this year, we are planning on making our main parachute in-house. Given empirical calculations from the drogue chute, which is off the shelf, this should have a conservative coefficient of drag value of 1. For the payload parachute, we're just using a flat sheet, which has a well-established coefficient of drag of around 0.8. We'll be doing ejection tests with these, with the Scottish Aeronautics and Rocketry Association on June the 3rd. But before then, we'll be doing tests to make sure that all of these parachutes are in line with the simulated values. So after deployment, it's important that the chord lengths are different between the main chute and the drogue chute so they don't get tangled with each other. It's also important for the drogue chute to be the longer one between the two, as this will allow more give in the time that the CANSAT will have to deploy after apogee. So the in-house parachutes, their shroud lines loop through the bridle, and this allows a stronger design because there won't be any weakness from knots in the elastic material. We're also looking at modeling different tests and such to see if we can improve any of this anti-tangling measures. Now I'll pass you on to Barnaby for some flight reliability.
In terms of testing the vehicle, we've completed FEA analysis of transverse loads on the fins and axial acceleration in the avionics bay, as well as a symmetric slice analysis of the vehicle in ANSYS fluid to validate drag coefficients from the other sources such as RASAROT and OpenRocket. We've updated our simulation models since CDR to reflect our change in body diameter, and we're now using fins, centering rings, and bulkheads made from water jet cut fiberglass sheets. In terms of confidence in the payload, we've taken advantage of the rapid prototyping that 3D printing allows to make a mock-up of our CANSAT design, from which we found out that the linear springs we were using were not strong enough to hold it up. This information prompted us to change our design from a linear spring to a torsional spring. Additionally, none of the 3D printed parts of the CANSAT are load-bearing during flight. Finally, we believe the high forces exerted by the springs on the solenoids, perpendicular to their axes, will increase friction to the point that they will not retract during flight and open the CANSAT doors inside the vehicle. This will be tested before the flight. Finally, flight analysis from RAS Aero 2 shows us that our vehicle is stable in flight at all speeds that we'll be traveling and far above, with a static margin between 2.2 and 3 between liftoff and Mach 1.8, and a maximum Mach number of 0.99. The static margin does not drop below 1.5 until Mach 2.5, which is well above the speed scope of this mission. I've been looking at a range of possible wind speeds and provisional launch angles. These are likely to change when considering CANSAT drift. The graph at the top of the slide shows the static margin of the launch vehicle at a Mach number between 0 and 1.5, and the graph at the bottom of the slide shows an altitude distance graph of the flight from RAS Aero 2 at a wind speed of 15 miles per hour and a vertical launch rod. The wind drift tests were completed with the conditions listed on the left-hand side of the slide. So far, the mechanical team have completed an integration test of the CANSAT avionics and structure and resized a few parts after measuring differences in sizing. A second integration test was successful, with the full CANSAT avionics fitting into their mountings. The avionics bay is very similar and has also been resized. An integration test for this is planned very shortly, as well as a full-size CANSAT fit test. For testing with the launch vehicle, we've planned an ejection test on the 3rd of June with SARA and GE rocketry. We also plan to test parachutes after they arrive and/or finish manufacturing as soon as the 3rd of June. Finally, we'll structurally test the vehicle after the ejection tests to ensure no damage has appeared as a result of the tests, and it still complies with technical regulations. Finally, in terms of manufacturing, we have the materials prepared and have some printing in progress for the CANSAT, as well as having raw materials collected for the launch vehicle. Everybody involved in composite manufacture has been adequately trained to use the labs and produce the components required. And now I'll pass you over to the electrical team, where they'll give you an overview of their design and their confidence in the flight.
Now moving on to the electronics design. Our PCB was finalized and ordered shortly after CDR with a few changes. We've switched from the CATS Vega as our COTS flight computer to the Eggtimer Quasar due to cost concerns and a few issues with the Vega. We have now completed our radio testing and it was very successful. So now we've moved to having 3 redundant ground stations because we found that omnidirectional antennas had enough performance as well. And we will be using the power channels on the main board to control the solenoids on the CANSAT. So these are the finalized PCBs that we were ordered. So we came up to 4 boards. The main board, you can see on the right, the GPS board, top left, payload board, middle left, and the interconnect board, bottom left. And on the right, you can see a 3D render of how they will be in the final position. The interconnect board is just so we can power our COTS flight computer without draining the batteries while we're on the ground using an umbilical. And then it will switch to batteries once the umbilical is removed. So we've changed our name from Firefly to Firefly from Phoenix, as we found out that was taken shortly afterwards. The payload has improved power efficiency now. The GPS, we've added some LEDs. The interconnect is finalized and finished. The main board, lots of changes, but now that's finalized. So here are the boards as they came to us from JLC PCB. So most of these were all assembled by JLC PCB partly, with us assembling some of the other parts. You can see the interconnect board there on the left, and in the bottom right, we've got some of the unfinished boards on the right, and some of the partly and completed boards on the left. So we have 2 main boards completely assembled, 2 GPS boards, and 2 payload boards completely assembled. We haven't assembled any interconnect boards yet, but that will come in the coming weeks. Now, our testing, we're going to start with the radio. We recently did our radio tests, and they were very successful. We managed to get a link over a 4.7 kilometer distance. Even using 2 omnidirectional antennas, we were able to send data back and forth. We are very happy with the performance of our radios, and it looks like they'll perform very reliably. The sensors, we've verified our GPS and pressure sensor. The altitude on the GPS wasn't great. However, we'll have the pressure sensor for that, and the pressure sensor is working great. The power, we've got all the basics tested, as well as the power switch, and the buzzer is very loud. We're still waiting on some more detailed testing, but for our purposes, this is good enough to fly.
So for our storage tests, we've confirmed that the SD card is working just fine. However, unfortunately for our flash, we were not able to communicate with it because of a timeout. But it's worth noting that because the HAL that we are using doesn't have support for QSPI, we have a manual implementation. So it is highly likely that it's just a quick software bug that needs to be worked out.
Now moving on to a few of the issues. We found that there was an issue with the mainboard power. There was a flipped capacitor. We've desoldered, resoldered that, works fine. And another issue is with our IMU. We've misconfigured it, so it is always off because the power is wired. So what we're going to do is we're going to desolder it, cut a trace, solder a wire, and resolder it. Due to the package of the chip, it's going to be quite difficult. But the IMU isn't actually mission critical, it's just a nice to have. Now, our to-do for testing. We need to finish the testing of our power systems, test the pyro channels with the solenoids, do the IMU fix and then test that, do a full radio test with multiple ground stations and multiple payloads, test the GPS more thoroughly, and test the pressure sensor more thoroughly. On the COTS side, we still need to assemble our egg timer board and test the ejection using the egg timer. However, we're very far along and all of our components seem flyable at this point.
Boom, I'm in another room and I'm going to be talking through our launch operations procedure. I'm not going to go through every single stage of this 14-point list, but I will highlight some key points, such as verifying the battery level, communications performance, and sensor performance of the avionics, and laying out the vehicle in sections to check chords, thus verifying the structural integrity of the body and the recovery system. Dangerous stages are highlighted in red. These are mainly the handling of explosive material. As soon as any of this is added to the system, there is a fire hazard and care must be taken. However, when we're handling it, that's when the risk is at its highest, and therefore greatest precaution is required. And this follows through in the preparation of the launch vehicle. Now consider the preparation of the payload. Much like the avionics, there is a requirement to verify the charge of the battery and communications test, with the option to swap out both of these components if necessary. Subsequently, the solar array arms are closed and the payload is integrated into the launch vehicle and plugged to umbilical power. Ground station mainly concerns itself with connecting itself to our live data streams and running a communication test with the integrated payload and avionics. Then test ground station tracking performance can be tested and switched to manual use if necessary. Then heading out to the launch pad, power cables should be removed as no one wants to fly the power cable attached, and the pyro interlock pin should be removed. This is not actually connected to pyro and is working as a technology demonstration for the interlock. Next, the motor needs prepared for launch by inserting the igniter and connecting to the launch system before retreating to a safe distance. After confirming contact with the ground station and activating GPS tracking, we're ready to wait for launch clearance from our RSOs. During launch, there's not much we can do other than monitor and log ground station data and cross our fingers and hope for the best. However, during descent, we are plotting GPS position in order to calculate a predicted landing location for the vehicle and the CANSAT. Then to recover these vehicles, we can use this predicted GPS location and the buzzers that are included on both vehicles to help our ground crews find the descended vehicles. Following that, data analysis is conducted and added to the post-flight review. I'll be handing you over to Neve to wrap up our flight readiness review.
So just to give a quick update on outreach, we will be doing an outreach session at Scottish Space School in June, which is an in-person event attended by 80+ high school pupils to encourage them to pursue a degree in STEM at university. So that'll be taking place in June. And finally, to conclude, our major accomplishments since CDR have mostly been our very successful range test. We've started some manufacture and some testing, and going forward, it's just full steam ahead on more manufacture and more testing. And finally, we'd like to acknowledge the Alumni Fund and JLPCB for sponsoring us this year, as well as GoFundMe sponsors from last year who funded our last few bits for this competition.